Good morning everyone. Welcome to this session. So in the last class we have seen the solution of elliptical partial differential equation, and we have seen that we have looked into a whole post problem, and we have seen that if there is if one condition is non-homogeneous and all other boundary conditions are homogeneous, we have to construct a standard eigenvalue problem in the direction where the boundary conditions are homogeneous, and then we have looked into some special type of boundary conditions, and then we have solved the problems to its completion. And we have already also seen that if there is a process which is occurring under steady state, that will be represented or modeled by an elliptical partial differential equation. Then what is left is that we have to look into the hyperbolic partial differential equation in rectangular coordinate system, and we will be solving a well post problem, because we already know that if an actual problem which is not well post all the time, it may be an ill post problem, and we have seen the techniques how to convert the ill post problem into an well post problem, and then we have to solve. Now in today's class, what we will be doing is that we will be solving a hyperbolic partial differential equation. Let's look into the hyperbolic partial differential equation. So we will be solving a problem del square u del t square is equal to del square u del x square, and at t is equal to 0, u is equal to u naught 1, and at t is equal to 0, del u del t will be is equal to, let us say, u naught 2, and boundary conditions are at x is equal to 0, we have u is equal to 0, and x is equal to 1, we have u is equal to 0. So if you remember, in case of hyperbolic partial differential equation, the conditions, two conditions are specified at t is equal to 0. So these are the Cauchy boundary condition, when both the boundaries are specified at the same boundary. Now what we will be doing next is that so this is a well post problem for a hyperbolic partial differential equation, where the initial condition is already set and it is both conditions are specified. So it is a well post problem because the boundary conditions are homogeneous. Now what we will do next, we will be looking for a separation of variable type of problem, and since the boundary conditions in the x direction they are homogeneous, we have to construct a standard eigenvalue problem in the x direction. So we assume that u is a product of two functions, one is function of time alone, another is the function of space alone. So we are going to substitute this in the governing equation. If we do that, we will be getting x d square t d t square is equal to t d square x dx square, and we divide by x t. So it will be 1 over t d square t dt square is equal to 1 over x d square x dx square. The left hand side is a function of time alone, the right hand side is function of space alone. They will be equal, and they will be equal to some constant minus alpha square, because if this constant is 0 or positive, we will be landing into a trivial solution. Now let us formulate the standard eigenvalue problem. 1 over x d square x dx square is equal to minus alpha square. So therefore d square x dx square plus alpha square x is equal to 0, subject to the boundary condition of the original problem in the x direction. That means at x is equal to 0 and 1, capital X is equal to 0. So this formulates the standard eigenvalue problem in the x direction, and we have already seen the solution of this equation. The solution is this is a standard eigenvalue problem with eigenvalues n pi, where the index n runs from 1 to infinity, and the eigenfunctions are sine functions. So let us look into that. So the eigenvalues are n pi, alpha n is equal to n pi n runs from 1 to up to infinity, and eigenfunctions are xn c1 sin n pi x. Okay. Now, let us, so that completes the solution of x varying part or spatial varying part. Now, we will be looking into the time varying part. So, let us look into the time varying part. 1 by Tn dTn dt square is equal to minus alpha n square or minus n square pi square. So, if we do that, so it becomes d square Tn dt square plus n square pi square Tn will be equal to 0. So, we will be looking into the solution of this. So, if this will be d square Tn dt square plus n square pi square Tn is equal to 0. So, as we have seen earlier, the solution of this equation will be the combination of sine functions and cosine function. So, Tn of t will be, let us say, C2 sin n pi t plus C3 cosine n pi t. Okay. So, let us look into the solution corresponding to nth eigenvalue. So, this will be nothing but xn Tn. So, it will be C1 sin n pi x multiplied by C2 sin n pi t plus C3 cosine n pi t. So, I take this inside. So, this will be sin n pi x C1 C2, it will be new constants, let us say C1 prime sin n pi t plus C3 prime cosine n pi t. So, complete solution becomes now summation superposing of all the solution n is equal to 1 to infinity. So, this will be summation of n is equal to 1 to infinity C1 prime Cn1 prime sin n pi x sin n pi t plus Cn2 prime sin n pi x cosine n pi t. So, that gives the complete solution. Now, there are two constants in this final expression, Cn1 prime and Cn2 prime, and we have two initial conditions which have remained unutilized. So, we will be utilizing these two conditions and see what we get. So, we utilize these two initial conditions in order to evaluate the constants Cn1 prime and Cn2 prime. So, u of x t is equal to summation of n is equal to 1 to infinity Cn1 prime sin n pi x sin n pi t plus Cn2 prime sin n pi x cosine n pi t. So, that is the complete solution. Now, we utilize the two initial condition at t is equal to 0, u is equal to u01. So, therefore, we write u01 is equal to summation n is equal to 1 to infinity. So, at t is equal to 0, sin 0 is 0 and cos 0 is 1. So, only one term will survive out of these two. So, this will be Cn2 prime sin n pi x. Now, we will be evaluating the constant Cn2 prime by exploiting the orthogonal property of the eigenfunctions. If we do that, I will be multiplying both sides by sin m pi x dx, and u01 is constant. So, it will be out. So, 0 to 1 sin m pi x dx is equal to 0 to 1 summation n is equal to 1 to infinity C n 2 prime sin n pi x sin m pi x dx. So, if we open up the summation series, all the terms will vanish, only one term will survive, that will be when n is equal to m. So, it will be 0 to 1 sin square n pi x dx. Next, I will be changing the running variable on the left hand side to n m from n to n. So, it becomes u 0 1 0 to 1 sin n pi x dx is C n 2 prime, and we have already seen that this integral is half. So, it will be C n 2 prime by 2. So, therefore, we can have C n 2 prime is equal to 2 u 0 1 1 minus cosine n pi divided by n pi. So, that will be the expression of C n 2 prime. So, next what we will be doing, we will be utilizing the other initial condition and to get the other constant C n 2 prime. Okay. So, the other condition is at t is equal to 0, del u del t will be is equal to 0. So, let us evaluate what is del u del t. Del u del t is summation n is equal to 1 to infinity C n 1 prime n pi sin n pi x cosine n pi t and minus C n 2 prime sin n pi x into n pi sin n pi t. So, that is del u del t. We evaluate del u del t at t is equal to 0. If you do that, then this term will vanish because sin 0 is 0 and cos 0 is 1. So, that will survive. So, I will be having C n 1 prime multiplied by n pi sin n pi x, and del u del t at t is equal to 0 is u 0 2. Okay. So, if you remember the original boundary initial condition at t is equal to 0, del u del t was u 0 2. So, we write u 0 2 is equal to summation n is equal to 1 to infinity C n 1 prime n pi sin n pi x. So, I multiply again, I will be exploiting the orthogonal property of the eigen functions and evaluate sin n 1 prime. So, I multiply both sides by sin m pi x dx and then integrate over the domain of x from 0 to 1. So, u 0 t is constant. So, this will be 0 to 1 sin m pi x dx is equal to 0 to 1 summation n is equal to 1 to infinity C n 1 prime n pi sin n pi x sin m pi x dx, and only one term will survive, all the other terms will vanish because of the orthogonal property of the sine function. Then I change the running index m into n. So, this will be giving you 1 minus cosine n pi divided by n pi, and on the right hand side I will be getting C n 1 prime n pi integral sin square n pi x dx, that will be nothing but half. So, C n 1 prime is nothing but 2 u 0 2 by n pi 1 minus cosine n pi divided by n pi. So, now we will be able to get the complete solution. So, if you look into the complete solution, the complete solution will be u x t is equal to summation n is equal to 1 to infinity C n 1 prime sin n pi x sin n pi t plus C n 2 prime sin n pi x cosine n pi t. Now, we will be substituting the value of Cn1 prime and Cn2 prime. So, this will be n is equal to 1 to infinity bracket 2 u02 by n pi 1 minus cosine n pi over n pi sin n pi x sin n pi t plus Cn2 prime is plus 2 u01 1 minus cosine n pi divided by n pi sin n pi x cosine n pi t. So, that gives the complete solution of u as a function of x and t for the hyperbolic problem we are dealing with. Next, what I will be doing, I will be taking one more example of hyperbolic problem where one of the boundary condition is having a non-homogeneous value. Then we will be breaking down this problem into two sub problems considering one non-homogeneity at a time, and then we will see how to get the solution of the sub problem and construct the complete solution. So, next example that we will be taking up is del square u del t square is equal to del square u del x square, where at t is equal to 0 I have u is equal to u01 and del u del t is equal to u02, and at x is equal to 0 I have u is equal to u1 naught and u1 naught is already there. So, let us say u3 naught, and at x is equal to 1 u is equal to 0. Okay. So, I have a non-homogeneity in the in one of the boundary condition. So, what I do as usual, I will be breaking down this problem into two sub problems considering one non-homogeneity at a time. So, I will be substituting I will be breaking down this problem into two sub problems such that u is equal to u1 plus u2, and the formulation of u1 is del square u1 del t square is equal to del square u1 del x square, subject to at t is equal to 0 u1 is equal to u01 and del u1 del t is equal to u02. So, those are the conditions at t equal to 0, at x is equal to 0 and 1 u1 is equal to 0. So, this is a very well posed problem of the hyperbolic partial differential equation, and we have already seen the solution of this problem. The solution of this problem is given by this expression. Okay. So, that is there. Next, we will be looking into the other part u2. u2 is del square u2 del t square is equal to del square u2 del x square, where at t is equal to 0 my u2 is equal to 0 del u2 del t is equal to 0, subject to x is equal to 0 I have u2 is equal to u3 naught, and at x is equal to 1 I have u2 is equal to 0. So, I will be considering one non-homogeneity at a time. So, therefore, we can say that that will be u2 is equal to 0 and del u2 del t equal to 0. So, in fact, there are three sources of non-homogeneity. So, we will be considering one non-homogeneity at a time. So, I can keep this non-homogeneity intact, u2 is equal to u01. And in the second case, I will be considering the other non-homogeneity. So, it will be divided into three sub problems, because there are three sources of non-homogeneity 1, 2 and 3. So, u3 will be del square u3 del t square is equal to del square u3 del x square subject to at t is equal to 0, u3 is equal to 0 and del u3 del t is equal to u2 naught, and at x is equal to 0 and 1 my u3 is equal to 0. So, I have to solve just one sub problem u2 or u3. u1 is completely solved earlier, and let us see how, because if you solve either u2 and u3, then you will know how to solve both individually each sub problem. Now, let us look into this u3. So, it will be depending on, so we will be having an initial condition which is 0. So, I will be getting this sub problem. Okay. So, the first one is so this we know how to solve this equation. So, this will be a standard eigenvalue problem in the x direction, and we have already seen how to solve this equation. So, therefore, if you look into the standard solution, the solution will be u3 x t will be nothing but summation of n is equal to 1 to infinity c n 1 prime sin n pi x sin n pi t plus c n 2 prime sin n pi x cosine n pi t. Okay. So, at t is equal to 0, at t is equal to 0, u3 is equal to 0. So, this will be equal to 0, and n is equal to 1 to infinity sin 0 is 0 is 0. So, c n 2 prime sin n pi x. So, now since this coefficient is 0, the associated constant will be equal to 0. Okay. Then we took the other one, del u3 del t is equal to 0. So, del u3 del t at t is equal to 0 will be giving you the value n is equal to 1 to infinity c n 1 prime n pi sin n pi x, and del u3 del t is equal to u2 naught. So, I will be having u2 naught summation n is equal to 1 to infinity c n 1 prime n pi sin n pi x, and I can evaluate c n 1 prime as u2 naught 1 minus cosine n pi divided by n pi, and there will be 2 over here and will be n pi. So, this way we can evaluate c n 2 prime and c n 1 prime. These will be evaluated by using orthogonal property, and we can construct the complete solution of u3 by substituting these two coefficients. Now, which will be very interesting to solve the problem of u2. Now, let us look into the problem of u2. Del square u2 del t square will be is equal to del square u2 del x square. At t is equal to 0, u2 is equal to u0 1, and t is equal to 0, del u2 del t will be equal to 0, and we have at x is equal to 0, u2 is equal to u3 naught, and at x is equal to 1 we have u2 is equal to 0. So, we will be having a non-homogeneous boundary condition here, and therefore, we can break down this problem into two sub problem. u2 is equal to u2s plus u2t. So, the governing equation of u2s will be d square u2s dx square that we have done earlier is equal to 0. At x is equal to 0, u2s is equal to u3 naught, and at x is equal to 1, u2s is equal to 0. We know the solution of this. Solution of this u2s is equal to c1x plus c2. So, at x is equal to 0, u2s is equal to u3 naught. So, c2 is equal to u3 naught. So, and at x equal to 1, u2s is equal to 0. So, it will be C1 plus C2. So, C1 is equal to minus u3 naught. So, the solution of u2s, which will be a sole function of x, is minus u3 naught x plus u3 naught. So, u3 naught will be nothing but 1 minus x. So, therefore, we can look into the solution of governing equation of u2t. u2t will be del square u2t del t square is equal to del square u2t del x square. At t is equal to 0, u2 is equal to u01. So, this will be u2s plus u2t is equal to u01, and u2t will be nothing but u01 minus u2s, and it will be u01 minus u3 naught into 1 minus x, that is u2t at t is equal to 0. Similarly, at t is equal to 0, del u2t del t equal to 0. So, at t is equal to 0, and even the del u2t del t will be equal to 0, because the special varying part, the time derivative of that will be equal to 0, and the boundary condition at x equal to 0, I have my u2t is equal to 0, and at x is equal to 1, u2t is equal to 0. So, we will be having a standard eigenvalue problem in the x direction, and we will be having a non-zero initial condition at t equal to 0, and del u2 del t will be equal to 0 at t equal to 0. So, we will be getting the almost similar type of solution. If you look into the solution, you can see that the solution will be something like this. U x t will be summation n is equal to 1 to infinity c n 1 prime sin n pi x sin n pi t plus c n 2 prime sin n pi x cosine n pi t, and we have two initial condition at t is equal to 0, u2 is equal to u2t. So, this will be u2t will be equal to u01 minus u3 naught 1 minus x, and at t is equal to 0, we have del u2t del t will be equal to 0. So, because of this boundary initial condition, one of the constants will vanish and the other constant will be surviving. So, this will be the solution of u2t. Then we will be adding up all individual solution and getting the complete solution. U is equal to u1 plus u2s plus u2t. So, that will be constructing the complete solution. Okay. So, that completes the solution of hyperbolic partial differential equation. I will stop here in this class. In the next class, I will be moving over to the radial polar coordinate, cylindrical polar coordinate system. Thank you very much.